Hello, welcome to our presentation on our project, string monitoring solution. We are Team 5 and our advisor is Dr. Raby.
This is our abstract. You can find this on the Senior Design Expo website, but I'll go ahead and read it for you. Solar farms are filled with many photovoltaic strings. Being able to collect data on PV strings will increase yield and lower maintenance. Although, monitoring is difficult due to the amount of strings and the cost of monitoring. This group's project is designed to monitor multiple strings at a low cost.
Here are a few things about our background. We all are electrical engineering majors and minoring in the electric energy and smart grid. We each have our full-time positions lined up after graduation. John will work at Duke Energy, Tyler at AES Ohio, and I'll work at Honda at the East Liberty plant.
This project's purpose is to deal with the main issue limiting PV string monitoring adoption, which is cost. By using open source hardware and removing the need for oversized CTs, we can cut the cost immensely, increasing adoption. String monitoring is needed to help allow quick identification of ground faults in the PV array, which increases inverter uptime and tech safety while lowering labor costs. It also allows us to determine the performance of the PV array and determine poor performing strings while also comparing solar production versus inverter performance. This together allows for a better yield because we will now quickly identify issues.
Ground faults are probably the biggest issue that we see in PV strings and out in the field for utilities in general. It typically happens when wires are damaged or they're just getting old, equipment's getting old. So thousands of people die each year from electrical injuries and another 30,000 from non-fatal electrical injuries. But the biggest thing, ground faults are when energized conductor meets ground and it's still trying to complete the arc or complete the circuit. So it starts arcing.
Our solution is to provide affordable metering that will broadcast its measurements to a web page. On the left is a picture of our web page with live feedback, and on the right is a picture of our devices within an enclosure.
So this is our basic design. As you can see in the left, there's the string 1 and 2. They're in parallel. They're more like the solar panels if you were seeing it in the field. They're in series with 2 current sensors each, a current sensor each, Hall effect. Below you can see that there's a step-down resistor to reduce current voltage for our sensors. We don't want to damage the Arduino and the sensors, so that's there. And then at the bottom we have a shunt resistor with an operational amplifier, so that's our voltage sensor, and it's all hooked to our Arduino. And this is this is the digital board representation. Solar panels on the top left again, and you can kind of see how we wired it together. Kind of see what the parts actually look like as well. And you can see on the top right, current sensors again, right there. So the voltage sensor towards the bottom. Before we didn't mention this, but there's an LED display. So out in the field, if a technician's trying to look at the device, see if it's reading properly, maybe with Pi or the Arduino and everything's going well, they can look at that and get the readings for their voltage and current. And then obviously you can see the Arduino on the left and how we hook that up. And this is the schematic of what we just showed you. So the representation was kind of so you can see what these tools and equipment look like, these pieces. And this is kind of more of a easier look to how we wired it and what it's actually going to. As you can see, everything's labeled on the Arduino where it's going to, and then the current sensors as well.
The Arduino's main role in our circuit is to power and communicate with the devices and relay the information back to the Raspberry Pi through serial. For troubleshooting purposes and live feedback, we've included an LCD screen to display the IP address of the website, the voltage, and the currents of the two PV strings. The picture on the right is a sample of our Arduino code. The Raspberry Pi is the central computer and the brains in our project. We chose a Raspberry Pi because they're an affordable microcomputer that have small power consumption. And this is important because the Pi is going to be powered by a solar battery, as our solution will be placed in a solar field. The Raspberry Pi powers and communicates with the Arduino, like we've talked about before, through serial, as shown in the picture in the bottom left. The Raspberry Pi runs Python code in order to do this communication. The data from the Arduino is then organized, exported to HTML format, and then loaded onto a web page server. A screenshot of our web page is shown on the right. The web page's address is the internal IPv4 address of the Raspberry Pi. The web page server and Python code run automatically when the system boots up, eliminating the need for us to access the Raspberry Pi to stop operating it. The Raspberry Pi was loaded with the following programs for our project: Arduino IDE for programming the Arduino, Python 3 to talk with the Arduino via serial, VNC Viewer to remotely control the Raspberry Pi, and Flask to create a web page server.
The design of the project allows the Arduino to act as the brains, sensing currents and voltages, which passes this data to the OLED display to immediately display locally, and to the Raspberry Pi for remote sensing. Looking at the budget, since we are not paying ourselves, we can neglect this cost. Our total cost is $312.85, which can be reduced in the future by mass manufacturing and bulk ordering of the material used in the project.
Here's our Gantt chart, our schedule as our year went. So right now we are in testing, lab testing, final testing, and starting presentations, which is really right now in the reports, big thing. But as you can see, in September and October was a lot of our research on how we wanted to do this, how we decided we wanted to do Arduinos and the Raspberry Pi. Initial designs were in November. Prototype construction was mostly, I would say, December into January, especially, really. And by then we were kind of doing some pre-testing and trying things out. And that's when design improvements came about and how we started really working on the, let's say, the Raspberry Pi and the screens and everything. And yeah. So testing, this was the big part. Hardware programming was tested in like say late January, just seeing that everything worked. So we applied current to our sensors at different amps to verify the Arduino was reading data correctly, and mimicking the current expected from the step-down resistor, so we can confirm the voltage was reading correctly. And a lot of that was, scaling things in Arduino and the Arduino code and changing it and trying to, kind of get it down and seeing how fast we could change, current and voltage and see how fast we could pick it up. And finally, site testing and final install. And I'll get a little more into that, but it was canceled due to university, concerns, and we thought it was best with COVID-19 not to do that. But our COVID-19 response was spectacular. So John created the prototype and did a lot of the testing. Peter worked on the Raspberry Pi of the aspect and was remoting in, while John had it plugged up, and I was working on a lot of the Arduino stuff, programming on the Arduino. But we had weekly meetings, and we kept in constant contact. At least one meeting a week, typically two, and they go on for hours. Daily communication via text and the Microsoft Teams chats. And like I said, we were able to enable the remote connectivity, so we could remote into the Raspberry Pi and do work while it was someone else's house. It was spectacular.
Due to COVID-19 restrictions, field testing will not be able to be completed, preventing us from verifying the project actually works and potential issues. While we cannot verify, we are confident that our project works as designed. Currently, the project is powered externally, limiting the locations it could be permanently installed. In the future iterations, we would install a charging circuit into the monitor and allow the monitor to be powered by the PV array, making the install easier. The project has a plus or minus 30-volt swing currently due to a small sensing current the voltage sensor has to read. In the future iterations, a less resistive resistor would be used to create a larger current, increasing sensing accuracy. If you have any further questions, feel free to reach out to our emails below. Thank you.